Alrighty then. Let's go. Hey guys, how's everyone going? Hope you're all having a good time tonight. Had some good weather, and we're also starting to get some relaxations of what we can and can't do. So it looks like we might be able to do our night sky tours probably from mid-June onwards, so that will be nice. If that's the case, what we'll be doing with our live streams of the night sky is we'll probably move those to during the week, so Wednesday, and we might do like one or two a month, just so you guys can keep on having a look at the night sky. All right, so if you guys, we've got a Discord channel down here in the bottom left. If you want to join and ask questions, you can do so in the description there. We've got a link to the Discord channel, so you can actually ask questions, and I'll answer them as we go along. And we've also got links to our social media, so you can keep up to date with what's happening at the observatory and what's happening in space. There's been a supernova in Messier 61 galaxy, so there is a place that's having a worse time at the moment than us. So we'll feel sorry for that small area around that star, and that's just blown up in Messier 61. So yeah, and there's also the link to our Patreon if you want to subscribe and get some cool stuff, and also help support the observatory as well. And if you can also like and share and this talk if you do like it, and also subscribe to us, and you get and click the notification bell there, and you get to notification on when we're going to go live. So we've got another live stream through the telescopes this coming Saturday, so hopefully the weather's good. Fingers crossed. We got our very first clear night after 6 weeks, perfectly clear night sky. Last Saturday, so we got to show some cool stuff as well there. All right, so we'll make a beginning with this talk. So we're going to talk about the Big Bang. It all started with a bang. So I took this title from Hot Chocolate. So it started with a kiss, but it started with a bang. So we're going to just discuss about the history, and also what's going to go on up to this point, and also what to expect in the future. So it's pretty interesting and how the universe has come about. We do have to take some notice that we don't really know a lot about the very beginning. We're hoping to find that out with telescopes like the James Webb telescope, which, please, for the love of God, does it get launched and opened correctly in 2021. I think that's now 12 years overdue, and about $8 to $9 billion over budget. But it's government. What do you expect? Also the square kilometre array, which is actually being built in the northwest of Western Australia, in South Africa, and some domes, some radio dishes in New South Wales, and I think also New Zealand. So that's what's called an interferometer. So you, instead of having one massive big dish, you have smaller little dishes. You combine them together, and you get the same power as a dish that big. So the square kilometre array is, if you has the same power. If you had one single dish, that's 1 square kilometre across. So we'll be able to. It's in optical observatories, you've got the European Southern Observatory in the Atacama Desert, and you've also got the Americans have got their Kilauea Observatory in Hawaii. They're considered the 2 best optical observatories in the world. This will be the same, but for radio telescopes as well. So we don't really understand a lot about what's happened in the beginning. It could have been the Big Bang could have possibly come out of primordial state of possible virtual particles. So this is getting really technical kind of stuff, but it is possible that there was a gravitational singularity at the very beginning, so a massive big black hole, and that black hole was the billionth of the size of a nuclear particle. So when we talk about that, we talk about an atom. So you've got the electrons and neutrons and neutrons and protons in the center of that atom. And everyone likes to think about this as, this is the beginning of the universe, but we really don't know whether it was like that, coming from one infinite point. But we think that we've got some scant details, but hopefully we can find that out over the next decades with all these cool observatories that we're getting. Dark matter and dark energy may have appeared at this point and been the catalyst for the expansion of that singularity into the Big Bang. And as that infinite universe expands, it starts cooling down. So it's extremely hot at in the very beginning. And as it expands out, that's when it starts to cool down. So we have over here we have the timeline of the universe. So we start off at the very beginning here with the actual Big Bang. Then we have this period of inflation where within a split second the universe expands incredibly fast. And then it slows down, and then you go through the phase of cosmic background radiation, which we've been able to see using the WMAP here. We have the Dark Age, where it starts to cool down, but the universe is completely opaque because there's gas. We then go through the area of the epoch of reionization, where the first stars and galaxies start to form and start punching holes through that gas, and so that light can escape and you can see everything. And then we get the universe expanding through, and you've got galaxies in our solar system, and we also start to see another accelerated expansion, which we've only found recently. We thought maybe what would happen is the universe would get to a certain point and then you'd get the big crunch, but we've actually found that the universe is expanding, and it's expanding even quicker, and this is where the ideas of dark energy have come into place. So within the first second of the Big Bang, the universe cooled from 10 to the power of 32 Kelvin to over about a billion Kelvin over this time. So very, very quickly. That is as hot as the core of a newly formed neutron star. So nearly about 100, it was cooled down to about 100 billion Celsius. So you wouldn't want to roast your turkey in there for 30 minutes, I tell you that. You've also got gravity, which keeps us to the ground, separating and operating in the universe. We have the strong nuclear force becoming a distinct own from the electro-weak force, and we have four fundamental forces in the actual universe today. So we have gravity that keeps you down to my seat. So I'm sitting. The Earth's gravity is pulling me down, and I'm not floating off from my seat. Electromagnetism, that is what's holding the atoms together to form a seat, and also to form me. If not the atoms that make me, make the chair, they would all go off, and you wouldn't have me, you wouldn't have the seat, you probably wouldn't have wouldn't have the computer and everything and also YouTube. We can actually see this electromagnetic interactions in in the computer monitor or the TV monitor that you're seeing, because it's responsible for the generation of the light that is allowing you to see me and also see the presentation as well. The strong nuclear force actually holds the atom together, so makes sure that the proton and the electron and also the electrons that's orbiting around are all combined. And the weak nuclear force also allows it to decay. So when you hear about, say, a radioactive element like radium or uranium or plutonium, and they say, oh, it's got a half-life of 35 years, well, that's to the point of where it's half its life has gone by. It's still got another 70 years if it's got a half-life of 35 years, which I think cesium does. So we now have, within the first second, the forces that we need for the universe to be like we are. We also, within the first second of the Big Bang, we see the inflation period occurs, where the universe expands by an order of 10 to the power of 26 in a split second. So just amazing speeds. Let's just say you don't have to worry about the police multinovas picking the universe up for speeding that quickly. After that, we've got elementary particles that will make up our atoms, make up the protons and neutrons, in what's called a Quark Glue plasma. So, and also after this rapid expansion, it still expands, but it's just not happening as a faster pace. And this is what a quark gluon plasma looks like, or a quark soup. And this is actually being created from this image here is actually being created by one of the national the American Brookhaven National Laboratory's relativistic heavy ion collider. So a smaller version of the Large Hadron Collider that's in Europe. And what's happened is they've fired two particles together, and you've had they've smacked into each other and had a massive big explosion, essentially. And the temperature is so much that the quarks that make up the atom, which we can see in this image here, we can see we've got the electron, we've got the proton and the neutron in the middle here. And if we go even further into here, into the atom, and we can actually see that we've got up quarks and down quarks that make up the proton and also the neutron. And there's also different flavors of them. The gluons are actually the interactions in between the quarks. Now, normally they can't escape the atom, but as you raise the temperature up, you get to temperature where plasma can form, and that's where the actual it's so hot that the electron can actually escape from the atom. But you can even go further and further, and with temperature, and the actual atom, the protons and neutrons actually melt away, and the quarks can escape, and the gluons can escape, and that is how we got a quark gluon. It's still so hot in there. We also then have the weak nuclear force escapes from the electromagnetic force, and so they're all now distinctive in their all the fundamental forces of nature are now operating as distinct forces. And so you've also got gravity now governing the expansion of the universe as well. So we're now looking into 10 seconds after the Big Bang. The universe is still a super hot glowing fog because of electrons and protons are hindering the emission. So this is called the combination area of the history of the universe. We then have 20 seconds after the Big Bang. So we still haven't even reached a minute. So it's quite amazing how quickly this has happened. And we've got nuclear fusion has ceased with normal amounts of matter. So you have 75% hydrogen atoms and 25% helium. And this is the fuel that stars need to form. You'll start off with a star which is mostly hydrogen, and then in the core it fuses that hydrogen into helium, and from there, the rest of the atoms, the elements that we see in the periodic table, are created from either explosions of stars or mergers of neutron stars, and so it's quite an amazing place, our universe. Free electrons, which are electrons that have been stripped away from atoms, ions, or molecules, are scattering around. So there's still not a lot of light being able to get out, so you can see. So if you were able to withstand it, it would just be like being in a massive big fog. That's what it would be like. Probably a little bit reddish as well. And now nothing really much happens till about 47,000 years after the Big Bang, and we start to enter the matter era. And we have the expansion of the universe is still decreasing, and it's at a faster rate. Now in 70,000 years after the Big Bang, matter now dominates the universe. We have matter, and we also have what's called antimatter. So we have instead of a proton, we have a positron, and instead of a proton being a positive charge, a positron is a negative charge. And so basically everything that we have is opposite, apart from neutrons. I think neutrons are still don't have a charge in antimatter. But if a proton and a positron actually match, you get a massive big explosion. It was funny that there was Angels and Demons have just come onto Netflix, and spoiler alert, it has something to do with the Large Hadron Collider starting up and causing them capturing antimatter in huge abundance, enough to make a bomb or so. But that is the reason. If you would get an explosion if you had antimatter and matter collide, it wouldn't be. It's not something that will blow up a city or anything like that, but or even blow up in your hands. But it would be when they do collide, they do extinguish each other, as we say. We then enter what's called the cosmic dark age. So similar to the dark ages of the Middle Ages. It's between when the first. This is where we're starting to come up to the point where the universe does become transparent. So this is considered between 350,000 years, 370,000 years to 342 million years after the Big Bang. And now the universe has cooled down to about 3,000 Kelvin, or 2,727 Celsius. So that's now cooled down just below, about 130 Kelvin below the boiling point of iron. So when we say cool down, it's a relative term. It's gone from absolutely white hot to iron will boil. So it's still not a nice place. It's still dark, still diffuse with dense obscuring fog of primordial gas. We see electrons combining to protons and neutrons to form atoms. So we're seeing more hydrogen and helium. Beforehand that was more primordial, but now we're actually starting to see complex atoms. And then we've also got an image of what this looks like, and this is an image from what we call the cosmic microwave background radiation, and this is an image that's taken from WMAP, or what we call the Wilkinson microwave anisotopic probe. and it's named after David Wilkinson, who was a world-renowned pioneer in the field of cosmology, specializing in the cosmic microwave background radiation. And what you're seeing here is not visible light that has taken so long to get here that what's caused what we call redshifted. And so you're seeing light that has moved from visible light to the microwave. And so we can see here we've got the light spectrum here. So we only really just see, this is what our eyes can only see, just this small sliver. We've got infrared here, which we can use to see people's temperature, just to see if they've got a cold or something, or we can see how hot a fire is burning. We've got microwaves here, which you can use to cook our food. We've also got our radio and TV signals here as well, which we use to listen to the radio or watch the TV as well. On the other side, we've got ultraviolet light that we have to put sunscreen on to protect our skin. We also have X-rays, which we can take photos if we've got a broken bone. And we've also got gamma rays here, which are really intense and can do a lot of damage to our DNA if it hits us as well. And so while we're saying redshifted, we're seeing the Doppler effect here, and we can see here in this little diagram, as this police car is coming up to the person, it sounds a lot higher pitched, and that's because the sound waves from the car are quite compact and are and coming towards us. As the police car moves away from us, the audio waves get stretched out, and so you get that whine sound instead of a high-pitched noise as the police car speeds away. So this is very similar to this is the same principle, because that light has traveled so far. It's moved with the Doppler effect into the microwave background, and so we're seeing here what the universe looked like. So these dark patches here are actually some of the holes that we're starting to see, and we can see some of the matter here. So still not a great place to be, but we're getting closer to what our universe will look like. We reach the epoch of ionization, and this is where the very first stars start to form. And they're called population 3 stars. They're massive behemoths. They're just so huge. So, some of the stars that we can I think the biggest one we've seen is VY Scuti, and if you put that in our solar system, it would gobble up all the planets, including Saturn. So you'd have Uranus and Neptune still orbiting around this. It's something like if you flew around the equator in a 747, it would take you nearly 10,000, something like either like 1,000 years or 10,000 years. That's how big it is. But these population 3 stars are even massive, and they're only made up of hydrogen and helium because there's nothing else in the universe. And so we start to see these stars. They only last several million years. They don't last, some of these big boys stars that we've got now, where they'll last 50 to 200 million years. These stars are only lasting anywhere between 1 to 5 million years, and then they just blow up because they're just so uneconomical. But not only do they see the universe with other atoms elements like nitrogen, oxygen, carbon, iron, calcium, and that in the process of blowing up, but they also blow away the dust so that the universe has a chance for light to escape, so that we can actually see through that fog. So we can have, this is a population 3 star, as we can see. We think we haven't been able to see them. There've been a couple of occasions where we've gone, oh, we found them, but we're still not sure. But we should be able to see these guys with the James Webb's telescope. So fingers crossed that telescope goes. But when they do die, they make elements as oxygen, carbon, and also silicon as well. And these elements will then seed the neighbouring gas and dust, and that will lead to the population 2 stars, which we call metal poor stars, and also gas giants as well, of gas giant planets. Population 2 stars have hydrogen and helium, but they don't have a lot of other elements like oxygen and carbon and silicates and all that kind of stuff. So you've gone from having stars that just are purely hydrogen and helium to stars that population 2 stars, which are hydrogen and helium plus a little bit of other elements as well. And when you get to our stars, which are population 1 stars, there's a lot more oxygen, silicates, and nitrogen and carbon that you can see in the light from our star. Yes, fingers crossed, St. John. What's clearing out. So not only are they exploding and clearing out that the gas, that gaseous fog, but the radiation coming off these stars, what we call the solar wind, is also helping to reionize the universe and poking holes as well through that gas and making the universe possible to be seen as well. So here we've got a photo of a globular cluster. I believe it would be 47 Tucana, which we can see in the southern hemisphere. It's right next to the small Magellatic Cloud. These are 12 billion-year-old stars, and so they're population 2 stars, and we can see by sending their light through a spectrum, so a prism, and causing the rainbow effect, we can then have a look at Fraunhofer lines, which are dark lines, to work out what type of elements are in that light that makes up the star as well. We also start to see the beginnings of galaxies. So they're not spiral galaxies or anything like this. This is a galaxy called GN-Z11. It's currently the oldest galaxy and the most distant we know. It's about 13.4 billion years old, and it's about 36 billion years old, 36 billion light years away from us. So it's very, very far. It's only about 4,000 light years across. So we're not talking about these big spiral galaxies where they're 100 like ours, where our galaxies are 106,000 light years across. They're very small. They still haven't gobbled each other up and to make much bigger stars as well. So this is around, we start to see this around 400 million years after the Big Bang. And so this is what it would probably look a little bit like we're starting to enter what's called the Renaissance age. So we're seeing that the galaxies and stars are blowing away that dust and also the gas, and we're starting to get massive big clumpings of what will form galaxies and nebulas as well. We start to see the beginning of our galaxy possibly, and we also start to see over this period of time the different types of galaxies. So this is now about 700 million years after the Big Bang. We start to see those smaller galaxies clump together, and we start to get spiral galaxies, which is a little bit like what we expect our galaxy to look like. It has a few more arms than this particular barred spiral, but we get irregular galaxies like we have with the Large Magellatic Cloud. We have the traditional spiral, which we've got in our, this is, I believe, the Pinwheel galaxy in the northern hemisphere. We have the southern Pinwheel galaxy in the southern hemisphere, which is called M83, and or Messier 83, which is where the French electronic band M83 got their name from. And we've also got other types as well. We've got the percular, we've got the elliptical, which is what will end up happening to our galaxy once it's merged with the Andromeda galaxy. So these tend to be coming towards the end of the galaxy's life. And we also have the lenticular galaxies as well, which they're a mixture of spiral plus elliptical. We also start to see around this time, 720 million years after the Big Bang, we start to see globular clusters form around the Milky Way's galactical core. So we think there's at least one which is Omega Centauri, which could possibly be the core of a dwarf galaxy that's orbit around, which is being captured by our galaxy, and that's had all the dust and gas stripped away, but it's just got its core. But the rest of the globular clusters that we see, we believe, have formed from gas clouds, gas and dust clouds that have existed above and below the disk. So you've got about 120 of these, 100 to 120 above the disk and below the disk as well, around that, to make up 100 to 120. So they're very, very old stars. There's the Omega Centauri is about 170 light years across and has about 10 million stars. 47 Tucana, which this image would be of, is between 1 to 2 million stars. But we've seen bigger as well. We've seen one, Merrill 2, which is around Andromeda, which is about 250 light years across, and we think has about 20 million stars as well. So it's, think of this as an active retirement village for stars. Open star clusters, which we can see on night sky tours and in the sky, they're primary school, kindergarten for stars. They're stars that are very, very young. But globular clusters are another type of star cluster where they're really, really old stars. And these are all generation 2 stars. We do start to see in some of them some formulation of where some stars have died, and out of that we've got new stars. And they're also self-separating as well. So if you get a star that is massive and it forms out in the regions here, it will actually migrate into the center, and the smaller stars that get formed out here actually get sent out to the outer regions as well. So within this area here, we haven't been able to find a planet around in a star cluster, in a globular star cluster yet. But if there was a planet around here, you would be looking at having no nighttime because it's just so many stars close. And even out here in the suburbs, where the radiation would be probably more palatable, but still quite deadly, you're still looking at twilight conditions. So it would be pretty interesting to be able to go to one of these and see exactly up close what it looks like inside. We also, 800 million years after the Big Bang, we can actually see the furthest extent of the Hubble ultra deep field. And this is an image of the universe where they didn't, in the Fornux cluster, which is in the southern hemisphere, and we thought it was complete. NASA and astronomers thought it was completely empty. And so the actual image was taken from September 24th, 2003 to January 16, 2004. They had this space coming up to Christmas and over Christmas where they didn't have anything planned for the Hubble Space Telescope. So they set its job to as it came into view, as it orbited around the Earth, to take photos of this one particular area. And they got essentially they took exposures, when you add them all up, is over 1 million seconds. And in this image, where they expect the nothing to be, they found an estimated 10,000 galaxies. And you've got to think about that. This is a 3D image, really. While it's on a 2D surface, some of these bigger galaxies, they're about 6 billion light years away. But the smaller and smaller you get with these galaxies, they're further and further away, to the point where they're, in terms of their age as well, some of these smaller ones are some of the very first galaxies that we'll ever get, that we ever get to see. And then there was another one that was taken called the Extreme Deep Field, and they actually found in that image approximately another further 5,500 galaxies as well, with some of the oldest being 13.2 billion years. And that exposure time was 2 million seconds. So they went even further than that. So, and to put that into perspective of how that small region it is, we've got here the extreme deep field, just this point here, and we've got the full moon. So in this photo here, you've got about 16,000 galaxies. And if you did further exposures, you'd probably even find more galaxies as well. So we're now entering 1 billion years, where we're starting after the Big Bang, and now we're starting to see a proper spiral galaxy here. And so this is the galaxy HCM 6A, and this is the most distant normal galaxy that we've observed in its state. So from this, we can actually work out, here is the disk, and you can see this is probably radio jets coming off the central black hole that's feeding on material as well. We also get to see that we've seen the oldest exoplanet, so a planet around another star. And this gas giant's called the Genesis planet, and its catalogue number is PSRB 1620-26b. So the PSR bit is actually the name of the star that it orbits, and then the B at the end is the planet itself. And it's got a mass of 2 times the weight of Jupiter as well. It orbits at a distance of 23 AU, so 3.4 billion kilometers from the star, and that's a little larger than that orbit is a little bit larger than the distance between Uranus and the Sun. So it does orbit quite a bit out. Its orbit takes about 100 years to complete. I think Uranus takes about 84 years, just off the top of my head. We also, 5 billion years after the Big Bang, the earliest population of the population 1 stars, so suns like us, with heavy elements saturated. And we also can see planetary disks appear around some of these stars as well, which will eventually lead to rockier planets, moons, asteroids, and comets. Rocky terrestrial planets take a lot longer to form than the big gas giants. It took a couple of 100 million years to form the Earth, where with Jupiter it took less than 100 million years. So it's, gas giants, when they get started, they swell up pretty big as well. 6 billion years now, we're starting to, after the Big Bang, we can actually start to see the wider structure of the universe as well. We can see great walls and sheets and filaments of galaxy clusters as well. So what this spider web is actually, you've got here where you've got the yellow bits. You can see that these are superclusters. So if you look, if you have quite a powerful telescope, you can, and you go out to the country, you can see some really nice galaxies in the Virgo cluster. It's even better once you've put your camera on, you can take some photos and take several images and then stack them together to get a really nice image. But this is where we get the term cosmic web of the universe. So usually they think our local group of galaxies in some of these little knots. We aren't particularly in a supercluster. We're in a local group of galaxies, and that's dominated by our galaxy and also the Andromeda galaxy. So the observable universe is looking more and more like what we see today. And then we enter the acceleration age, and this is where the universe speeds up again. And this is where the velocities at which the current galaxies are receding away from us. So we see some galaxies, will be moving towards us, like the Andromeda, but that's because you've got a local group of galaxies that are gravitationally bound to each other. But when we look at galaxies that are much further away, we see them actually speeding up and accelerating away from us. And this was only discovered back in 1998. And this has been found by looking at specific type of supernova called a Type 1a supernova. And we're still trying to find out why this is happening. We know this is where the term dark energy is. Why is it just suddenly expanding out? So it is quite an interesting, if you are looking to go into astronomy, cosmology, this is something you can look at. Brian Schmidt, who now is the Chancellor of the Australian National University, was part of this research as well. So the way this works is that we use a Type 1a supernova as a standard candle. The explosion is always the same because it's a white dwarf that's orbiting around a parent star, just like in here with this video. So you can see that there's the gravity around the white dwarf is a lot more than the parent star, and it's going to start leaching off material. And this is a video that's been done by Castro, which was a Australian program, and it's going to go blow up right now. Now, a white dwarf can exist until and with material falling onto it until it gets to about 1.44 times the mass of our sun, and then it hits the limit, what's called the Chandrasekhar Limits. And Chandrasekhar was a very, very famous Sri Lankan astronomer, physicist, who'd worked out this limit. And so because it always hits this limit, the explosions are the same. So we can then use it. Okay, we've worked out that this is a Type 1a supernova in this galaxy. Okay, so that's bright. But we now see another one which is a little bit fainter than in this galaxy over here. And so we can actually see that this galaxy is further away from this galaxy. And then we can also see that light and see how whether it's coming towards us or also going away from us. So we can see that it's expanding out as well. We can see the makeup of the universe here. So we have 5% normal matter, which is us, Earth, stars, nebulas, galaxies. Then we have 26% of the universe is dark matter. And so again, we don't even know what, this is, we don't know what it is, so we can't see it, but we know it has an effect because it keeps galaxies from ripping themselves apart because galaxies are spinning too fast. But they are thought to be non-baryonic in nature, and possibly composed of as yet undiscovered subatomic particles as well. Again, the dark energy, it's unknown, but it is, it's another interesting, if you want to do, if you do want to go into astronomy, this is another exciting area, and you can do it here in Western Australia as well with Curtin or UWA. We also see in this time 9.2 billion years after the Big Bang, a supernova has possibly triggered the nebula that formed our solar system. And you can see here that 32 million years after that supernova, the sun forms, and you've got the planetary disk. And this is one that we've seen of another star that's been taken from the ALMA telescope in the Atacama Desert, this is of a planet, the protoplanetary disk of a star called HL Tauri, and so you can actually see that there's gaps in this protoplanetary disk, and this is where planets are forming. So it's a pretty interesting time to be alive in that system there. 1 million years after the sun's formed, we start to see the gas giants form. So you can see that as it's orbiting around, the planets are sucking off material from that protoplanetary disk and forming. 23 million years after the sun forms, that's when we start to see the Earth form as well. 66 million years after the sun forms, we get the moon, and that comes from a collision from the Earth and a planetoid that's the size of Mars called Theia, which we claim. So there is some thought now that we might have actually at one point had two moons, because on one side of the moon it's quite thin, its crust, and on the other side it's a lot thicker as well. So we've got a question here from Tony saying, if the galaxy is expanding, the universe is expanding, how is it that Andromeda is moving towards us? Well, we're seeing what we can actually see is, if we go back here to the cosmic web here, you can actually see the structure of the universe forming here. So you've got galaxies that are passing along these webs into superclusters. So these are galaxies in here that are gravitationally held to each other. So that we've got a local group of galaxies that will eventually become, so we'll merge with Andromeda, but in the process, the dwarf galaxies that are orbiting around Andromeda and dwarf galaxies that are orbiting around the Milky Way will combine as well. And as we progress further on into the future of the universe, these groups of galaxies will come together. But in the process, as the universe is expanding, these filaments these superclusters are actually moving away from each other as well. So they're just, for that effect to happen on local groups of galaxies, there hasn't been enough time in the universe for the universe to expand for that to occur. So now we come to the point over these next millions of years, and even today, where it is, where we exist as the universe is now. So we can actually see here the collision of Theia into the Earth. And you did not want to be there on the Earth at that time. And out of that material, the Earth would form a nice ring, and out of that would cause the moon to eventually make up as itself. And we can actually work. This is an idea that actually came out of the Apollo missions through a moon physicist by the name of Bill Hartman, who came up with the idea after ideas like well, maybe the moon was captured, maybe it formed next to the Earth as the Earth was forming, or maybe it was flung off from the Earth because the Earth was rotating so quickly. Because as you bring the moon closer to the Earth speeds up, just like a figure skater moves their hands. And what we were noticing was when we saw the rocks from anorthosite rocks, which were brought back from Apollo 15, from the original crust, we could see that the makeup of the moon was very similar to the Earth, but not the same. So a lot of the heavy elements that flew into that ring fell back onto Earth, and left the other chemical elements to know that we did have at some point a shared existence. Thankfully, this does happen because you get quite a large moon, which keeps the Earth quite stable in its axis. If we didn't have the moon, over thousands of years, the Earth would wobble. You could actually get, at some point, the tropics being at the Arctic or Antarctica area. So it's not we get the tides as well. And also, out of that collision, Earth gets gets the iron core from Theia as well, and you also get the having this, because it's got all this iron core in the middle, it's got a very strong magnetic field which protects our atmosphere from being stripped away by the sun's radiation or solar wind. And we can see this has had an effect on other planets like Mars, Venus as well. Venus actually has like a dust tail as it orbits around the sun, because it doesn't have a strong magnetic field. And Mars has patches of magnetic field, and it's had so much of its atmosphere stripped away that it's got 1% of Earth's atmosphere as well. So we're now looking into the future. So but the Andromeda Galaxy will merge with our galaxy, or a hostile takeover, in about 4 to 4.5 billion years. There's still they're now probably leaning towards 4.5 billion years, so we've got an extra 500 million years by ourselves. But that collision will take another 4 billion years to settle down into a nice shaped elliptical galaxy. So they'll collide, they'll come back together, they'll deform each other, and then eventually meet ourselves. So you've got one big galaxy. Between 100 billion and a trillion years, our local group of galaxies will all merge into one large galaxy. So we'll all be together. One of us. Now it does get. I would like to say it all goes on merry on our way, but once we get to about 800 billion years, the galaxies and brightness starts to decrease, because most of the stars are now red dwarf stars. So the smallest of the stars, and some of these, and you've also started to get the red dwarfs. There's been enough time in the universe for them to die and become what we theorize as black dwarfs. So we think that red dwarfs have a life of about 100 billion years. So think of these as probably like the Priuses. Yes, resistance is futile. Especially with the galaxies, yes, mergers. And so you as the stars are also getting smaller and smaller as they go. So you've had the very big behemoths at the very start, which are like your Hummers. They go through their fuel very quickly. Then you've got our sun, which is like a common sedan, and now with the red dwarfs, you've got your Priuses, your hybrid cars as well. 2 trillion years after the beginning of the Big Bang, galaxies outside, the universe is expanded so much that the local supercluster is no longer visible, and 100 trillion years after the Big Bang, or from now, you've got star formation will end. So now you'll start to see the actual universe start to completely cool down now. between 10 decillion to 1 decillion years, protons and neutrons start to decay. After 10 decillion years, black holes are now completely dominating our universe. But even they have an end. The Hawking radiation, because they're not feeding and getting bigger, they're starting to evaporate via Hawking radiation, named after Stephen Hawking. And after 1 gagoo years, all the black holes have evaporated, and you have an empty universe. And so it's going to end like that, completely dark. So I'm sorry to leave it on such a dark ending, pardon the pun there. If you've got it, I hope you've had a lovely time watching this presentation. If you have any questions, please leave them in the chat, and we even after the stream, we can answer them. And please join us on Saturday for our live stream of the night sky. Even if it's cloudy, we have images that we'll have taken during the week, so we can at least still look at the night sky. And if you've liked this presentation, please like the video, please share it with your friends. I'm sure it's better than reruns of MasterChef or My Kitchen Rules. But also, and if you do like what we do, please subscribe, click the notification bell so you get notifications on when we do this. And also, if we know it's hard times, but if you feel that you want to help support the observatory, the volunteer group runs the observatory for the government now to keep the history alive. It's 120 years, coming up to our 125th birthday next year. So it's the old girl's looking pretty good, and we're getting back into research as well. So if you want to be a part of that, please subscribe through our Patreon, and we give you some presents as well. And thanks very much, guys, for joining tonight, and hope you enjoyed, and we'll see you next time. Bye.